Hi everybody, welcome to my 5th axial bar video. In this video I'm going to be talking about the normal forces inside the bar and the displacements of the bar under different areas and different modulus of elasticity. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos, specifically number 2 to number 10. Alright, let's get into this. So in order to analyze what the elongations are of this bar to fill out this graph here, we first need to find the normal forces in the bar, because we know that we need to find every variable of this equation here, NL over AE. Alright, so we need to find the normal forces in each one. We know the length of each one. The areas we can find because we're given the two diameters. And the E, we know that because it's given. We got aluminum here and steel here. Alright, so let's first go about calculating the areas. So whenever I see something like a diameter, and I know that later on I'm going to need the area, I like to go ahead and calculate it right away. Because later on, if you need to calculate your area, you're like in the middle of all your equations and you need to do like pi r squared and pi d squared, and I just like to find those first. Find all the preconditions first and then just use those values to plug them back in later on. So let's go ahead and calculate these areas. So we know that the area of this second piece, A2, is going to be pi r squared. So pi, we're given the diameter, that's the radius, the radius is the diameter by 2, squared, of course, that goes to A2 equals to pi by 4, because this 2 squares the 2 down there, you pull the 4 out, and then d2 squared. Alright, so I've done the math, and the first area, or the second area, comes out to be 0.00785 square meters. Alright, box that off. There we go. And by the same principles, A1 is 0.0314 meters squared. Alright, so let's do a quick reality check. Does this make sense? We know that this is twice as much as this, and we're squaring it. So that means that this one here should be about 4 times bigger than this. You know, twice the value squared. And that's true. If you take this number, you divide it by 4, you'll get that one. Alright, let's move on to internal forces. So as we can see on our diagram here, we have 2 applied forces. One right here and one right here at the joint. Now these joints are soundly connected, alright? They're not going to come apart or anything funny like that. So we have a change in conditions here. We need a cut here. Alright, cut 2, we'll call that. We keep on going. Oh, change in condition here. Both a change in area, a change in E, and a change in force. Whereas here it was all the same. Alright, so here 3 things are changing, so we definitely need a cut. Alright, let's get into the free body diagrams. Alright, let's do section 2 here. Alright, we got this going on. We have applied force here, 100 meganewtons. That's a lot of newtons. And of course, we're going to have internal reaction here, and 2. Don't forget your directions, always important. Although somebody reading your work doesn't know what you mean when you say sum of the forces in the x. So we can see N2 equals to negative 100 meganewtons. Alright, I'll move on to free body diagram of the first section here, this piece. Alright, so we've got a cut section. Like that. We're going to have N1, and we also have 2 other forces here. 100 meganewtons here. Let's draw it like this. 100 meganewtons here. Alright, again, quick draw in your directions. Sum of the forces, the x equals 0, and N1 equals negative 200 meganewtons. Alright, so let's just go ahead and plot these on our normal force graph here. So, section 1, this piece, oh, that's negative 200. So we'll just pick an arbitrary distance down. Call it negative 200 meganewtons. In the second piece, we found it goes up to negative 100, so that's half here. There we go. Alright. Okay, so you could start making some assumptions about what this graph is going to be. You might look at this and say, oh, this is like greater, like bigger, so this is going to be like quite a bit steeper slope than this piece. But can't really make that assumption yet because we have different moduluses of elasticity in different areas, so it might change before the end of the day. Alright, let's get into the elongation here. So the total elongation is equal to the sum of the elongation of each individual part. So that means the elongation of this whole bar is equal to the elongation of this piece plus the elongation of that piece. Alright, so I'm just going to call it delta 1 plus delta 2. Alright, now the displacement for delta 1 has to do with all the properties that delta 1 or section 1 has. So using this equation over here, we write it all out again. So delta total equals to internal force in 1, length of 1, E of 1, and A of 1, plus N2, L2, E2, A2. Alright, and now that we've defined our variables, we can go in and plug our values in and to solve for the answer. Alright, so N1, negative 200 meganewtons. And like I've said before, I always like to put them in terms of just meters or just newtons. Take the prefixes out of your data crunching and your number crunching there. That will make sure that your answer comes in meters instead of having to decipher through, you know, what a meganewton divided by a millimeter is. Just put it all in terms of meters, newtons, and you'll get your answer in meters, and from there, if you want, you can convert it back. Times the length of the first piece. That's 1.2 meters, right? Or E of the first piece, that's aluminum, 70 GPa, right there. So it's 70 times 10 to the 9. And A of the first piece. Well, we just calculated that before, A1, 0.0314. Alright, and same thing for the second piece. N2, negative 100. Let's have a length, 1.5 meters. Modulus of elasticity, steel, 200 GPa. And the area less than the area first area. We see that it comes out to be this. Alright, now I've ran these through in my calculator, and the total equals to negative 0.109 plus a bit of this piece here. Alright, now you see how I've calculated this set, I've collapsed it down to one number, this set, I've collapsed it down to that number. That makes it easier later when we want to calculate the elongations at different points. Because we know delta 1 is this, is this, is this. So delta 1 is equal to this, and delta 2, how much delta 2 is elongated is this. Alright, and then delta total, you can just add them up to find the total elongation. At the very end of the bar, it turns out to be negative 0.205 meters. Alright, let's just box that off. There we go. Delta total. Alright, let's go back and plot this. So the delta 1, the delta at this displacement here, would be this equation here evaluated at delta 1. So basically we just take delta 1. Alright, and that's negative 0.109. Alright, so let's just pick a point here. Okay. And the delta total is negative 0.205 meters. Alright, so it's a little bit further down here. Alright, not quite double the distance. So this one here is going to have a slightly steeper slope. Alright, and this one here is slightly shallower. There we go, it looks just like this. Alright, if you're wondering how to figure out which one is steeper, you can just take this depth here divided by the length, you get the slope. And then you take this amount here minus this amount divided by the length, and you'll get two different slopes. I mean, it's pretty close, but in this case it turns out to be that one is greater. Alright, I can give you those values for the slope. So for the first one, it's m equals to negative 0.09. This one, m equals to 0.064. Alright, so this one's not quite as steep as that one. Alright guys, that pretty well sums up this video. So we have an example where everything is changing. We have different forces in each one, different lengths, different areas, different moduluses of elasticity. So we went through, we pre-calculated our areas. Like usual, we made a cut every time there was a change in conditions. We did our free body diagrams, neatly labeled the forces, summed them up, found the normal forces in each piece. We realized that the elongation was the sum of the individual elongations of each piece. So the elongation of this piece plus the elongation of that piece is the total elongation. And then we wrote each one out in terms of its individual parts, plugged in the numbers, and there we go, got that. And of course we graphed it, just like this. Alright, thanks so much for watching guys, I hope this helped you out. See you in my next video.